The changing chemistry of Earth's atmosphere. One source. This chapter from CamScanner, April 21, 2025, 15.28, PDF, examines the changing chemistry of Earth's atmosphere since the dawn of time, with a focus on the rapid alterations occurring in the last 2 centuries due to industrialization and human activities. It identifies and explains key global environmental changes, such as stratospheric ozone depletion, acid deposition, urban air pollution, and enhanced global warming, detailing their causes and far-reaching consequences for the planet's ecosystems and human health. The text discusses specific chemical processes and reactions involved in these changes, particularly concerning ozone and acid rain, and presents data and scientific understanding of these atmospheric issues. Ultimately, the chapter underscores the significant human impact on the atmosphere and the urgent need to understand and address these alterations.
What are 4 key issues of environment changes? Based on the sources, for the most significant global chain phenomena that our atmosphere is currently experiencing include stratospheric ozone depletion. This involves the thinning of the ozone layer, which protects the Earth from damaging solar ultraviolet radiation. Acid deposition. This refers to the increased acidity of rainfall and dry deposition, which can damage forests and aquatic life. Urban air pollution. This encompasses the presence of harmful substances in the air in urban areas, leading to respiratory and ocular distress. Enhanced global warming. This is the increase in the Earth's average temperature, primarily due to increased concentrations of greenhouse gases. These phenomena are largely attributed to anthropogenic, human-induced, changes in the chemistry of our atmosphere. Understanding these issues is crucial for predicting the future implications for the Earth's fragile ecosystem. What are some root causes of 4 key phenomena? Based on the sources, the root causes of the 4 key environmental chain phenomena are primarily anthropogenic, human-induced, changes in the chemistry of our atmosphere. Here's a breakdown for each phenomenon. Stratospheric ozone depletion. The primary root cause of stratospheric ozone depletion is the anthropogenic increase in the levels of trace gases that catalyze the destruction of ozone in the stratosphere. Specifically, the sources identify chlorofluorocarbons, CFCs, which are increasing levels of chlorine in the upper atmosphere. Nitrogen oxide, NOx, emitted from supersonic transports were also an early concern. Additionally, other anthropogenic sources of nitrogen oxides, like the use of nitrogen fertilizers and large-scale burning of forests and grasslands, contribute to increased levels of tropospheric ozone, which can indirectly affect the stratosphere. Halons, containing bromine, used in fire extinguishers also contribute to ozone depletion synergistically with chlorine radicals. The increase in greenhouse gases warming the lower atmosphere can also lead to a cooling of the stratosphere, which at colder temperatures can increase the effectiveness of ozone-destroying processes involving polar stratospheric clouds, PSCs. Acid deposition. The main cause of acid deposition is the increased acidity of rainfall and dry deposition resulting from human activities. This increased acidity is primarily due to the release of sulfur oxides, SOx, and nitrogen oxides, NOx, into the atmosphere, mainly from the burning of fossil fuels in industrial combustion engines and automobile transport, as well as from industrial and agricultural practices. These oxides are converted in the atmosphere to sulfuric acid, H2SO4, and nitric acid, HNO3, which then fall to the earth as acid rain or dry deposition. The sulfur content in coal and oil is a significant contributor to sulfur dioxide emissions. Urban air pollution. Urban air pollution results from the presence of harmful substances in the air in urban areas, leading to respiratory and ocular distress. The sources indicate that this is largely due to trace gases related to increased industrialization and intensive agricultural practices. More specifically, it is linked to emissions from industrial and automobile transport. This includes primary pollutants directly emitted from sources, as well as secondary pollutants formed through chemical reactions in the atmosphere. Examples mentioned include ozone O3, nitric acid, and peroxyacetyl nitrate, PAN, which are key components of photochemical smog formed under conditions of high levels of nitrogen oxides and non-methane hydrocarbons in the presence of sunlight. The burning of fossil fuels also releases various harmful particulates and gases. Enhanced global warming. Enhanced global warming. The increase in the Earth's average temperature is primarily caused by the increased concentrations of greenhouse gases in the atmosphere due to human activities. The most important naturally occurring greenhouse gases are water vapor and carbon dioxide. However, anthropogenic activities, particularly the combustion of fossil fuels, have led to significant increase in the atmospheric concentrations of carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and chlorofluorocarbons, CFCs. These gases absorb and re-radiate infrared radiation emitted by the Earth, trapping heat and leading to a warming of the planet. Industrialization, intensive agriculture, and deforestation are major sources of these increased greenhouse gas emissions. The relative importance of different greenhouse gases in contributing to global warming depends on their atmospheric lifetime and their global warming potential, GWP, with gases like methane and CFCs having significantly higher GWPs than CO2.
Key impacts of these four phenomena on human health. Based on the sources, here are some key impacts of the four identified environmental change phenomena on human health. 1. Stratospheric ozone depletion. The thinning of the ozone layer leads to an increase in damaging solar ultraviolet (UV) radiation reaching the Earth's surface. Increased exposure to UV radiation is linked to a higher incidence of cataracts and suppression of the human immune response. It also significantly increases the risk of non-melanoma and potentially melanoma skin cancers. Studies have shown a correlation between increased UVB light and higher rates of non-melanoma skin cancer incidence at lower latitudes. A small percentage decrease in stratospheric ozone can lead to a disproportionately larger increase in biologically damaging UV radiation and consequently skin cancer incidence. UVB light can damage DNA by affecting the pyrimidine bases. This photochemical modification of DNA can have deleterious biological consequences. Increased UV radiation may also lead to increased susceptibility to bacterial and viral infections due to immune suppression. 2. Acid deposition. While the sources detail the damage of acid deposition to forests and aquatic ecosystems, the direct impacts on human health are not as explicitly outlined in these excerpts. One indirect impact mentioned is the potential for acid deposition to contribute to pollution problems that affect human health. For instance, acid precipitation is connected with other pollution processes leading to the formation of nitrogen and sulfur-based oxoacids and aerosols, which can cause respiratory hazards. The sources primarily focus on ecological consequences like damage to forests, waldsterben, and the acidification of lakes and soils. 3. Urban air pollution. Urban air pollution causes respiratory and ocular distress. The high levels of harmful substances in urban air, often related to industrial and automobile transport, are associated with a significant price tag of health risks and increased human health care costs. Specific components of urban smog such as ozone O3, nitric acid and peroxyacetyl nitrate PAN, are linked to respiratory tract damage. Small airborne particles, less than 2.5 micrometers in diameter, in urban air pollution can be inhaled deeply into the respiratory tract, posing a threat to human health. These particles, often generated by fossil fuel combustion, can contain toxic organic species and have been linked to various health problems. Historical examples like the pea-soup fogs in London, which were characterized by high levels of sulfur oxides and smoke, resulted in significant increases in mortality and respiratory illnesses. Modern urban smog, dominated by photochemical smog with components like ozone, still causes respiratory distress. 4. Enhanced global warming. Enhanced global warming is expected to lead to a wide spectrum of health risks arising from phenomena like desertification, rising sea level, and changing weather patterns. While the sources acknowledge the significance of enhanced global warming for the planet's ecosystem and climate, the specific details of direct impacts on human health are not extensively discussed within these excerpts. Further information in Chapter 13 mentioned in the text likely elaborates on these aspects.
What actions humans should implement to end these four environment phenomena? Based on the sources, here are some of the key actions humans should implement to address the four identified environmental change phenomena. 1. Stratospheric ozone depletion. Regulation and phase-out of ozone-depleting substances. The sources highlight the success of international treaties in banning or restricting the manufacture and use of chlorofluorocarbons, CFCs, and other halogen-containing compounds like halons. The Montreal Protocol on substances that deplete the ozone layer is cited as a successful example of international cooperation to ban the further manufacture and use of CFCs. This suggests that continued adherence to and strengthening of such international agreements are crucial. The reduction in CFC emissions is expected to lead to a gradual recovery of the ozone layer over time. 2. Acid deposition. Reduction of sulfur dioxide, SO2, and nitrogen oxide, no emissions. The primary cause of acid deposition is the release of SO2 and NO from the burning of fossil fuels in industrial combustion engines and automobile transport. Therefore, actions should focus on reducing these emissions from power plants, industrial facilities, and vehicles. This can be achieved through technological advancements in emission control, such as scrubbers in power plants and catalytic converters in vehicles. Transitioning to cleaner energy sources that do not rely on the combustion of sulfur-containing fossil fuels is also a fundamental step. 3. Urban air pollution. Control of emissions from industrial and automobile transport. Urban air pollution is linked to trace gases released by increased industrialization and intensive agricultural practices, particularly emissions from industrial and automobile transport. Implementing stricter emission standards for vehicles and industries is essential. Promoting and investing in public transportation, cycling, and walking infrastructure can reduce the reliance on private vehicles. Development and adoption of cleaner technologies and fuels for vehicles and industrial processes can significantly decrease the release of harmful pollutants. The establishment and enforcement of ambient air quality standards that regulate key pollutants like ozone, O3, nitrogen oxides, sulfur dioxide, and particulate matter are important. 4. Enhanced global warming. Reduction of greenhouse gas emissions. Enhanced global warming is primarily caused by increased concentrations of greenhouse gases like carbon dioxide CO2, methane CH4, nitrous oxide N2O, and CFCs due to human activities, especially the combustion of fossil fuels. The most critical action is a significant and rapid reduction in the emissions of these greenhouse gases. This requires a transition away from fossil fuels, coal, oil, and natural gas, towards renewable energy sources such as solar, wind, and hydropower. Improving energy efficiency in all sectors, e.g., transportation, buildings, industry, can reduce overall energy demand and thus lower emissions. Addressing emissions from agriculture, such as methane from livestock and nitrous oxide from fertilizers, through sustainable farming practices is also necessary. Preventing deforestation and promoting reforestation are important as forests act as carbon sinks, absorbing CO2 from the atmosphere. In conclusion, addressing these 4 key environmental phenomena requires concerted and sustained efforts at individual, national, and international levels. These efforts must focus on reducing the anthropogenic release of harmful substances into the atmosphere through technological innovation, policy changes, and shifts towards more sustainable practices in energy production, transportation, industry, and agriculture. The success in tackling stratospheric ozone depletion through international cooperation on CFC regulation provides a model for addressing other global atmospheric challenges.
Welcome to the Deep Dive. Today, we're tackling something pretty fundamental: the actual air we breathe and how human activity is really changing its chemistry.
It is. Our mission today, based on the material we've looked through, is to give everyone a clear, hopefully insightful look at these shifts.
And why they matter. Right.
Yeah.
I mean, this isn't just abstract science. It connects directly to our lives, our environment.
Absolutely. It's quite striking. The Earth's atmosphere, it's always been changing, it's dynamic, but the speed of change in the last couple of centuries, it's unprecedented.
And the sources we reviewed, they really point towards human actions as the main driver here.
Overwhelmingly, yes. They identify 4 main areas, sort of interconnected areas of global atmospheric change.
Okay, let's break those down. So we're looking at, number 1, the thinning of that ozone layer way up high.
Stratospheric ozone depletion.
And then there's acid rain, or acid deposition, as the sources call it.
Making rain more acidic, yes.
Third is the pollution in our cities, smog.
Urban air pollution, including that ground-level ozone problem.
And finally, the big one, the warming of the whole planet, enhanced global warming.
That's the quartet. And they are definitely interconnected.
Sounds like a lot, but we're going to try and unpack it, show how it fits together, focus on what's really crucial from the material.
Exactly. The science behind it, the consequences we're seeing, and importantly, some of the efforts to actually address these things. They are covered in the sources.
So where should we start? Maybe with that shield high above us, the ozone layer.
Good place to start. That invisible layer, mostly ozone, OGO, way up in the stratosphere.
Between about 10 and 50 kilometers up, right?
That's the zone. And it's absolutely critical. Think of it like Earth's natural sunscreen.
Filtering out the really nasty ultraviolet radiation from the sun?
Especially UVB. The sources really hammer home how vital that filtering is for protecting life, plants, animals, us.
And the alarm bells really started ringing around, when was it, 1987?
Yeah, that's when the concern became really significant, the realization that this protective layer was being damaged.
And the villains of the story were these chemicals, CFCs.
Chlorofluorocarbons, CFCs, yes. They were used everywhere, weren't they?
Seemed like it. Refrigerators, aerosol sprays.
Yeah.
Seen as these sort of miracle inventions at first.
They were stable, non-toxic down here. But the problem was when they drifted up into the stratosphere.
Right. And the sources get into the chemistry, mechanism a third, they call it?
Yes, it's a catalytic cycle.
Yeah.
A single chlorine atom, broken off from a CFC molecule by UV light, can react with an ozone molecule, destroying it.
But it doesn't stop there, does it?
No, that's the scary part. The chlorine atom is then released again, free to go and destroy another ozone molecule.
And another, like a tiny wrecking ball, as you said. Just keeps going.
One chlorine atom can destroy thousands, tens of thousands of ozone molecules. It's incredibly efficient.
Wow. That discovery was huge, right? It led to a Nobel Prize.
It did, yes.
Yeah.
For understanding that atmospheric chemistry. Then, in 1985, the evidence became impossible to ignore.
The Antarctic ozone hole.
Exactly. The data was shocking. A massive loss of ozone, over half gone since the early 80s, appearing every Antarctic spring.
Late September lasting into December, specifically at certain altitudes 15 to 19 kilometers up.
Yes. The material shows graphs illustrating this dramatic dip in total ozone over Halley Bay, for instance.
So why Antarctica? Why was it so much worse there?
Well, the unique conditions there are key. Extreme cold in the winter allows these special clouds to form high up.
Polar stratospheric clouds, or PSCs.
PSCs, yes, made of ice crystals or nitric acid hydrates. And these clouds provide surfaces, sort of like little platforms, for chemical reactions to happen much faster.
Reactions involving chlorine and bromine, too, right?
Yeah.
Mechanisms
Well,
5 and V.
Precisely. These reactions convert inactive forms of chlorine into highly reactive forms.
Okay, so the clouds set the stage. What happens next?
Then, when sunlight returns in the Antarctic spring, it provides the energy to kickstart the ozone destruction cycles using that activated chlorine and bromine.
And there's something called the polar vortex involved, too.
Yes, the polar vortex. It's like this huge, stable whirlpool of intensely cold air circulating high above the pole in winter.
Which traps the air.
It isolates the air inside it, keeping it extremely cold and allowing those PSCs to persist. It basically contains the chemical reactor.
Fascinating. But it wasn't just an Antarctic problem, was it? The sources mentioned thinning elsewhere.
That's right. While the whole over Antarctica was the most dramatic, measurements showed ozone depletion happening at mid-latitudes, too.
Where most people live.
Exactly. Declines of maybe 1% to 6% per decade were observed in the late 80s. And there were questions about how the polar loss might be connected to or influencing mid-latitude ozone levels.
So less ozone means more UVB gets through.
That's the direct consequence. A thinner ozone shield lets more of this harmful UVB radiation reach the surface.
And the sources are pretty blunt about what that means for us. Health risks.
Definitely. Increased risk of skin cancers, both non-melanoma and the more dangerous melanoma. The data suggested a link even then.
Yeah, I saw a figure linking DNA's absorption spectrum with UVB, showing how ozone loss increases the radiation that directly damages our DNA. Pyrimidine dimers, it mentioned?
Precisely. It's direct biological damage at the molecular level.
Yeah.
Not just skin cancer, but also increased risk of cataracts.
Clouding of the eye's lens.
Yes. And potentially suppression of the immune system, making us more vulnerable to other diseases.
And it's not just humans. The environment suffers too.
Oh, absolutely. The material points to potential damage right at the base of the food chain, like phytoplankton in the oceans.
Which could impact fisheries.
Potentially, yes. Plus damage to agricultural crops, effects on other plants and animals. The biological consequences are widespread.
It sounds incredibly bleak, but this story actually has a relatively positive turn, doesn't it?
It does. It's actually one of the major environmental success stories. The international community got together.
The Montreal Protocol.
The Montreal Protocol, signed in 1987, and its subsequent amendments. It led to a phase-out, essentially a ban, on the production and use of the worst offenders, the CFCs and other ozone-depleting substances.
A rare example of global cooperation working.
Widely seen as such, yes. Now, CFCs last a long time in the atmosphere, so the effects linger.
Recovery is an instant.
No, but the ozone layer is recovering. Projections suggest it should return to pre-1980 levels around the middle of this century. It shows that decisive, global action based on science can work.
That's genuinely encouraging. Okay, so from the stratosphere, let's come down closer to Earth and talk about acid deposition, acid rain.
Right. Another major change linked to emissions. It's about increased acidity, not just in rain, but also snow, fog, and even dry particles falling out of the atmosphere.
And it's caused mainly by sulfur and nitrogen oxides.
Primarily, yes. Sulfur dioxide, SO, and various nitrogen oxides, NO. These get released from burning fossil fuels, industrial processes, even agriculture.
The sources mention that even normal rain is slightly acidic, pH around 5.6.
That's right, because carbon dioxide naturally dissolves in rainwater, forming weak carbonic acid. But acid rain is significantly more acidic than that.
So how do these pollutants make it so much more acidic? There are chemical reactions involved? Equations 20 to 22 in the material?
Yeah, basically SO and NO dissolve in atmospheric water droplets and react further, often involving oxidation to form sulfuric acid, H agarose, and nitric acid.
And those are strong acids.
Very strong acids, yes. They dramatically lower the pH of the precipitation.
Where do these SO and NO gases mainly come from?
Well, NO mostly comes from high-temperature combustion. Think car engines, power plants.
Okay.
And so primarily comes from burning coal and oil that contains sulfur as an impurity. The amount varies. Some coal is much higher in sulfur than others, as the material notes.
And the impacts are pretty severe, especially on ecosystems. I remember reading about Waldsterben in Germany.
Forest death, yes. A stark example. Acid deposition can directly damage leaves and needles on trees.
But it also affects the soil.
Critically, it leaches essential nutrients like calcium and magnesium out of the soil, making it harder for trees to grow.
And it does something with metals.
Yes. It can mobilize toxic metals like aluminum, which are normally bound up in soil minerals. These then get into the soil water and can harm tree roots and aquatic life.
So it gets into lakes and streams, too.
Definitely. Acidification of lakes and streams was a huge problem, especially in areas with geology that couldn't buffer the acid well. It led to fish kills, disrupted food webs, really damaged freshwater ecosystems. There's a figure showing the pH of rain over the eastern U.S., highlighting the affected areas.
And it's not just nature, it damages buildings, too.
Yes, particularly buildings or monuments made of limestone or marble, which are calcium carbon.
Like statues or old cathedrals?
Exactly. The sulfuric acid reacts with the calcium carbon, that's equation 23, basically dissolving the stone surface over time. Causes erosion and loss of detail.
The sources also touch on atmospheric aerosols, tiny particles. They can be acidic, too.
They can, contributing to dry deposition. Plus, these fine particles are a health hazard themselves, contributing to respiratory problems and reducing visibility, creating haze.
It really shows how interconnected things are, which brings us neatly to urban smog.
Another form of air pollution, one that people in cities often experience very directly.
And the sources differentiate between two types, London smog and LA smog.
Right. The classic London smog was more about smoke and sulfur dioxide, often in cool, humid conditions, what they call reducing smog.
Okay.
Los Angeles smog, on the other hand, is photochemical smog. It needs sunlight. It's characterized by high levels of oxidants, especially ozone.
And that's the one we're focusing on, the LA type driven by vehicle emissions.
Primarily, yes. Specifically, the formation of tropospheric ozone near ground level.
Now, this is confusing. We just talked about losing ozone high up being bad, but having ozone down here is also bad.
Exactly. It's all about location. Stratospheric ozone, good, protective. Tropospheric ozone, bad, a pollutant.
Okay, so how does this bad ground level ozone form?
It's not emitted directly, mostly. It forms from chemical reactions in the air. You need nitrogen oxides, NOx.
From cars and power plants again.
Yes. And volatile organic compounds, VOCs.
VOCs, what are those?
Things like unburnt fuel vapors, solvents, emissions from vegetation even, a whole range of organic chemicals that evaporate easily.
So, NO hues and sunlight.
Sunlight is the key ingredient. It provides the energy to drive the reactions equations 3 and 4 in the material, show a simplified version that cook up ozone from these precursors.
And the amount of ozone you get depends on the mix. The ratio of VOCs to NO.
Absolutely. The chemistry is complex. The sources include a figure, those ozone isoplith diagrams, showing how different concentrations of NO, aero, and hydrocarbons lead to different ozone levels. It's not always straightforward. Sometimes reducing one precursor might even increase ozone, depending on the ratio.
Tricky to control, then, and the effects. Why is ground-level ozone bad?
It's a strong oxidant. It irritates the respiratory system, can trigger asthma attacks, reduce lung function. It's particularly hard on vulnerable populations. Also causes eye irritation.
And it damages plants, too.
Yes, it can damage leaves, reduce crop yields, harm forests. It's a significant stressor for vegetation.
And besides ozone, smog includes other nasty stuff, too.
Oh, yes. Particulate matter, soot, dust, tiny aerosols is a major component and health concern. Carbon monoxide, CO, more sulfur dioxide, SO Euro, nitrogen dioxide, NO itself, mostly from combustion sources, all contributing to poor air quality and carrying various health risks.
Right. Okay. That covers smog. Now let's tackle the fourth big issue, the one that's perhaps the most globally encompassing enhanced global warming.
Indeed. The steady increase in the Earth's average temperature.
First off, the basic greenhouse effect is natural, even essential, right?
Absolutely. Certain gases naturally present in the atmosphere, mainly water vapor and carbon dioxide, trap some of the heat radiating from the Earth's surface. Without this natural greenhouse effect, the planet would be freezing. Way too cold for life as we know it.
Like a planetary blanket.
A good analogy, yes. It keeps the temperature livable.
So enhanced global warming is too much blanket.
Essentially, yes.
Yes.
It refers to the additional warming caused by the increased concentration of these greenhouse gases in the atmosphere, primarily due to human activity since the Industrial Revolution began.
And the main culprits are?
Carbon dioxide, CO, is the biggest contributor overall, mostly from burning fossil fuels and deforestation. But there are others. Methane, COH.
From agriculture and natural gas leaks?
Right. Nitrous oxide, NO, from fertilizers and industrial processes. And even those CFCs we talked about earlier, they're potent greenhouse gases too, although their concentrations are lower.
The sources had those graphs, figures 7.9 and 7.1, showing the concentrations of CoYo, methane, NORO, and CFC11 just climbing steadily.
A very clear upward trend, especially for K, which stays in the atmosphere for a very long time.
Then there's this concept of global warming potential, GWP.
Yes, that's important. It compares the heat-trapping ability of different gases relative to co-Euro over a specific time period.
So some gases are much stronger pound for pound, so to speak.
Exactly. Methane, for example, has a much higher GWP than co-Euro over shorter timescales. And some CFCs have GWPs thousands of times higher. So even small amounts can have a significant warming effect.
And the main sources of these increased emissions are pretty clear.
Very clear from the material. Burning coal, oil, and natural gas for energy and transport is the largest source of CARO. Deforestation reduces the planet's ability to absorb co-Euros. Industrial processes release various gases. Agriculture is a major source of methane and nitrous oxide.
And the potential consequences outlined in the sources, they're extensive.
They really are. Melting ice is a big one. Polar ice caps, glaciers worldwide. This contributes directly to sea level rise.
Threatening coastal communities.
Absolutely. We're also looking at changes in precipitation patterns. Some areas getting wetter, others much drier, leading to floods and droughts.
More extreme weather events.
An increased frequency and intensity of things like heat waves, heavy rainfall, possibly stronger storms. The warming puts more energy into the climate system.
And huge impacts on ecosystems, agriculture, human societies.
Disruption across the board, yes. Species struggling to adapt, shifts in growing seasons, challenges to water supplies and food security.
But it's complex, isn't it? Predicting exactly how much warming and where the impacts will be worst. The sources mention uncertainties.
Very much so. The Earth's climate system is incredibly complex, with lots of feedback loops.
Like water vapor. Warmer air holds more water vapor, which is itself a greenhouse gas.
That's a key positive feedback, yes. Melting ice reduces the planet's reflectivity, the albedo effect, causing more warming. Clouds are a huge uncertainty. They can have both warming and cooling effects depending on the type and altitude.
So it's not a simple cause and effect chain.
Not at all. It involves the interaction of the atmosphere, oceans, ice, land surface, and living things. That interconnectedness is crucial.
That seems to be the running theme here, interconnectedness.
It really is. All these issues, ozone depletion, acid rain, smog, global warming, They aren't entirely separate boxes. They interact, and often they share common root causes in human activity.
So wrapping this deep dive up, the material we've gone through paints a really clear picture, doesn't it? Humans have significantly altered and are continuing to alter the chemistry of the atmosphere we depend on.
Unmistakably. We've touched on the stratospheric ozone story, the damage, the consequences of increased UV, and the success, thankfully, of the Montreal Protocol.
Then acid deposition, damaging forests, lakes, even buildings, driven by sulfur and nitrogen emissions.
Followed by urban smog, particularly that harmful ground-level ozone cooked up from pollutants and sunlight, affecting our health directly.
And finally, the overarching challenge of enhanced global warming, driven by greenhouse gas emissions, with its potential for really far-reaching and disruptive consequences globally.
And the common thread, as the sources consistently highlight, is the impact of industrialization, energy production, transportation, agriculture, essentially, modern human civilization.
It certainly leaves you with a lot to think about regarding our collective footprint. As you, our listeners, go about your day, maybe take a moment to consider this invisible, vital atmosphere and the profound changes underway.
We hope this discussion, drawing on the detailed material we examined, has given you a clearer framework for understanding these critical environmental issues.
Perhaps it might even spark an interest in digging deeper into solutions, policy actions, or just how these changes might play out in the future. Thanks for joining us on The Deep Dive.